Hey, welcome back to Math with Patrick. Today is October 5th, and we're solving problem 278 from the Daily Epsilon calendar. And the answer today should be 5. And when there aren't really instructions here, it's assumed that we're solving for this x right here. So we have some rules about this x and y. It looks like they're both elements of the natural numbers. That just means that they're numbers like 1, 2, 3, 4, and just kind of counting up almost until infinity. So x and y can't be zero, they can't be negative, they can't be decimals or fractions. And it looks like we have some equation here where x to the power of 4 plus x squared is equal to 651 to the power of y minus 1. And this is a little bit strange just because we can't really solve for one of these variables. I mean, we could, right? We could add the one to the other side and then do I don't know, log base 651 of all this is equal to y. And that is possible. But then we're still left searching with this kind of difficult question of what values of x and y satisfy this equation such that they're both natural numbers. So I don't think solving for one of the variables is going to be the right thing to do here. Knowing that they are going to be natural numbers, I think the best thing to do here is to try to find some factors of these numbers and even factors of these expressions. So I think I will add that 1 to the left side here. And I'll just keep the right side the same. And I guess I want to do something a little bit strange. I want to try to factor this expression right here. It is a degree 4 polynomial, so a little bit tricky. I do think the trick here is to try to add an x squared. And so we're going to put an x squared right there, and then subtract an x squared. And then here I'm kind of setting myself up for a difference of squares factoring. The thing on the left is a perfect square. This is going to be x squared plus 1 squared. And then this minus x squared just kind of can stay put. And I'll just wait to deal with that 651 until later. And now that I do have a difference of squares, I can write this in a factored form. And again, the goal here is to think of these numbers in terms of factors or divisors, because that's usually a good strategy whenever you're working with only the natural numbers. So if I have a squared minus b squared, I know that I can write it as a plus b and a minus b. And a in this case is just what's on the inside of these parentheses, so x squared plus 1, x squared plus 1, and then b is going to just be that x right there. And so maybe to write it in standard form, I will swap that 1 and that x. So I will get the factors x squared plus x plus 1, and then x squared minus x plus the 1. And so this is equal to 651 to the power of y. I think it would be useful to find some factors of 651 as well. Here I can see that their digits add up to 12, or its digits add up to 12, and therefore it is a multiple of 3. So we can figure out what happens when we divide by 3. We could get 2 hundreds, and then 3 goes into 51 17 times. And so we know that 651 is going to be 3 times something, well, 217. But I think I can factor that one as well. It's a little bit harder, and I'm just going to reach for my calculator at this point, and I'm just going to do some trial division here. Looks like 13 doesn't work. What number was it? It's not 11. Is it 17? No, of course not. 31? There we go. Okay, so it's 7 and 31. So times 7 times 31. Not sure why I didn't just check 7 in the first place, but oh well. I guess that would have been obvious had I realized that it's 21 times 10 and then plus a 7, but whatever. Okay, and now I have some kind of factored form here. One thing I do want to show is that these two numbers here are coprime, which basically means that they don't share any factors. For example, 20 and 15 are not coprime because they have a common factor of 5. But say the number 15 and how about 4 are coprime? Because yes, they are composite numbers, but they don't share any prime factors. And this is important because then I want to show that we essentially have to divvy up this 3 7, and 31 into different piles. So let's assume for a sec that we do actually have a common divisor of these numbers, and we'll just call it d. So we'll assume that d divides x squared plus x plus 1, and also d divides x squared minus x plus 1. To just kind of use an example with actual natural numbers for a sec, we could say that 3 divides 15, and 3 also divides 21. And one fact is if you have two numbers that are divisible by another, their sum and difference are also divisible by that number. Just like a quick example, right? If I do 21 minus 15, I get 6. If I do 21 plus 15, I get 36. And both of those are multiples of 3. So that's what I'm going to do here. If I'm assuming that I do have some divisor here, then this divisor also must divide their sum, which will be 2x squared. These terms cancel out, plus a 2. And it should also divide their difference. So I'm going to use these arrows right here to kind of show that one statement implies the other. They're going to divide their difference. The first and last terms cancel out, and then x minus negative x is 2x. From here, I can make more claims. This divisor that we have supposedly divides this expression. And again, just using natural numbers as an example, if I have a number that divides another, then I know one of two claims. Either it divides, well, one factor, or it divides the other. Clearly, this one isn't true, but it was true that this 3 divides one of the factors of our original number. So being able to factor this expression here, I know that d divides either 2, because again, I'm kind of factoring it like this right now, or d divides x squared plus 1. And then let's do it for the second one as well. D divides 2, or d divides x. So if d divides 2, that means one of two things. D is equal to 1 or D is equal to 2. And that's basically it. And then we get those same conditions right here. D is either equal to 1 or D is equal to 2. Or maybe it's the case that D divides this number or that number. And one thing I do know, though, is that one of these two things needs to be true, and also one of these two things needs to be true, right? Because this was a true statement and that was a true statement. So I need to find some kind of truth here or here, but then also here or there. And so there's essentially 4 different conditions that I'm working through. Either this is true and that is true. And so either D is equal to 1 or 2. Either this is true and that is true. But then still we're left in this case of D must be equal to 1 or 2. The only thing that really is different is if I choose this example and this example. But if both of those are concurrently true, if D divides x and then also x squared plus 1, D must be 1. Because if, say, for example, D divides x, we could just pick some numbers here for a sec, like 2 and 4. This claim over here just wouldn't be true anymore. D would be still 2, but then x squared plus 1 is 16 plus 1. So this divisor would clearly divide that first number, but then it wouldn't divide anything one more. And so if I hold both of those claims to be true together, then that must force D to be equal to 1. So I have essentially 2 conditions here. Either D could be 1 or D could be 2. But if we do look at our original numbers, I think these are always odd. Because if we try plugging in some numbers just to test out the parity or the even or oddness of these 2 terms, we're always going to get an odd number. Because if, say, we plug in an even number here or here, an even number squared plus another even number is even. And then finally adding a 1 makes it odd. And then same thing kind of goes here. We get an even number here, and then adding the 1 would make it odd. And then if we try plugging in an odd number, say like 3, we would get an odd number here plus an odd number here, and that's back to being even. And then adding the 1 makes it odd. So both of these factors are forced to be odd numbers, and so I can't have D being equal to 2. Overall, this shows that if I do have a common divisor of the first 2 factors here and here, that common divisor is forced to be 1. In other words, they're co-prime. They don't share any common factors. So all of this was to show that when we do this factoring right here and set it equal to this expression on the right, I can't share the 3 and the 7 between both of these factors because they're co-prime. And so kind of splitting up that exponent for a sec, 3 to the y times 7 to the y times 31 to the power of y. All of these different factors must be present in these ones, but in separate factors. As in, for example, I can't put a 3 and then like a 7 squared over here, and then a 3 and then a 31 squared over here, because they share this 3 together. And so we get something kind of interesting. Over here, I'm noticing that the 31 is pretty big. And maybe we could think of it real quick as just like 21 to the power of y times 31 to the power of y. As we increase y, this term is going to grow significantly faster than that one. That's just kind of how exponential expressions behave. But if we look at this side, both of these numbers are actually going to kind of grow at the same speed. Thinking in terms of limits for a sec, if we took the limit as x went to infinity over here and just kind of arbitrarily made a ratio out of these two factors, this would tend to 1. Basically, I'm just looking at the ratio of the leading coefficient here, and it's just 1 divided by 1. Over here, if I try the same thing and I put the smaller one over the bigger one and think, okay, what's the limit as y goes to infinity here, this is going to tend to 0. I'm kind of looking at it as just a fraction like this, and multiplying something between 0 and 1 to itself over and over and over again will give us a 0 eventually in limit world. So essentially what I'm saying here is that as x and y grow, these two factors get closer together relatively, whereas these two factors grow apart. So to me, maybe that's like a heuristic justification for that. Once I find one solution to this problem, I know I don't need to keep looking further, because it's going to get more and more impossible to have the values of these things, which are growing apart, to match the values of these things, which are relatively growing together. So all we really need to do is find some natural number x and some natural number y that both satisfy this equation here. Clearly, the easiest thing to pick for y is 1, because that's our first natural number. So I'll just say y is equal to 1 just to test it out. Maybe let me swap the positions, because I'm noticing that this will be our lesser term. So here's the 31, here's the 21. So 31 times 21 should be equal to this. And we could just try, again, plugging in some numbers for x just to see what happens, starting with 1. If we plug in 1, it's 1 plus 1 plus 1, and then 1 minus 1 plus 1. And clearly 3 times 1 doesn't fit the bill. Noticing that that was a small number, maybe I'd skip up to 3 or even 4. Let's try 4. That's 16 plus 4 plus 1. And so this does give us 21. But then doing 16 minus 4 plus 1 only gives us 13. And that's not going to match. So we could try 5, and this should be the one that works. 25 plus 5 plus 1 is 31. And then 25 minus 5 plus the 1 is 21. And so this does match when x is equal to 5 and y is equal to 1. And I did all of this other work with divisors and coprimality, don't know if that's a word, just to show that we don't need to keep looking for other solutions. Because if we pick, say, y is equal to 2 for a sec, these two numbers would be super far apart. This is going to be, 441 and then 961. I'm already noticing that this is more than double the other one. Whereas these two numbers are going to grow closer and closer together as we guess like larger and larger values for x. Again, just to show an example, if I plug in, say, 10, I will get 100 plus 10 plus 1, so 111, and then I will get 20 less than that, so 91. And so as x gets larger, these two numbers are relative in size, getting closer and closer together. So to me, that's enough of an example to show that we're never going to find another solution to this problem. We're just going to stop here. Also, I think it's a little bit silly, but if this were, say, like the like maybe non-negative integers greater than or equal to 0, I think we could just plug a 0 and 0 and 0 in here, and then we would get 0 equals 0. So it is kind of important that we are working in the natural numbers, which exclude that number 0. So either way, we're all done, and we know that we found the one and only solution for today's problem. So thanks for watching, and I'll see you tomorrow.